path described by electron in transverse magnetic field. Okay, path described by electron in transverse magnetic field. Let capital B be the magnetic induction flux density. Let capital B is the magnetic induction flux density. Okay, capital B be the magnetic induction flux density of uniform magnetic field acting perpendicular and into the plane of paper. Okay, a beam of electron each of mass m and carrying negative charge moving with velocity v in a horizontal direction enters the magnetic field at O. As shown in the figure. Then since B and B are at right angles to each other, V and B are at right angles to each other, the magnitude of the magnetic force exerted on the electron is given by F equal to EVB. This is the equation number first. The direction of this force is always perpendicular to the plane. Okay? At V and B, the direction as given by Fleming left hand rule as shown in the figure. Okay, since force is always perpendicular to velocity, it only changes the direction of V and not speed. Therefore, the electron describes a circular path of radius capital R in the field. The constant radial force produces the centripetal acceleration of the electrons. Okay. Then applying Newton's second law of motion, F equal to mv square by R, where applying Newton's second law of motion, where R is the radius of a moving electron path. Okay, this is equation number second. Okay, equation first and second we get from equation first and second we get EVB equal to mv square by capital R. This is equation number third. The radius of the circular path is given by R equal to mv upon EB and speed V equal to EB capital R by M. This is equation number 4. This is equation number 4. And this is equation number 5. Okay. Since the motion of circular time for one revolution, the period t is given by t is 2 pi r by v. 2 pi r by v, that is 2 pi by v, 2 pi by v, and mv by ev. V is cancelled out by v, then time period t is 2 pi m by eb. Okay, this is equation number 6. And the frequency of revolution in the orbit is given by frequency of revolution in the orbit is given by f equal to eb by 2 pi m, eb by 2 pi m, because frequency is inversely proportional to 1 upon time period. Inversely proportional to time period. Okay, kinetic energy of revolving electron in transverse magnetic field is given by kinetic energy is 1 by 2 mv square, that is 1 by 2 m, the value of b is eb capital R by m whole square, that is e square b square r square by 2 m. This is equation number 7. Equation number 7. This is equation number 7. This is equation number 7, and this is equation number 8. This is equation number 8. This is equation number 8. Okay. Work done. Work done. The work done W on the electron by the electric field in moving it from the cathode to anode is given by W equal to charge. W equal to charge multiply potential difference. Multiply potential difference. Potential difference. Okay. Potential difference. Okay. Equal to EV, the kinetic energy acquired by the electron is given by kinetic energy acquired by the electron is given by 1 by 2 mv square, and equating we get, and equating we get EV equal to 1 by 2 mv square, then speed v equal to under root of 2 ev by m, 2 ev by m, where capital V is the potential difference. Potential difference. Small v is the speed of electron. Okay. Speed of electron. Then this is the expression for speed acquired by an electron as it reaches the anode. Okay. Next study. Magnetic deflection sensitivity. Magnetic deflection sensitivity. Magnetic deflection sensitivity. Magnetic deflection sensitivity. The deflection sensitivity of magnetic deflection. The deflection sensitivity. The deflection sensitivity of a magnetic deflection of a magnetic deflection. The deflection sensitivity of a magnetic deflection. Cathode ray tube is defined as the amount of spore of spot, the amount of spot deflection on the screen, spot deflection, deflection on the screen, deflection on the screen per unit magnetic flux, per unit magnetic flux, per unit magnetic flux density, density produced by the magnetic deflection, magnetic deflection whiles, okay. Magnetic deflection sensitivity. The deflection sensitivity of a magnetic deflection cathode ray tube is defined as the amount of spot deflection on the screen per unit magnetic flux density produced by the magnetic deflection wires. Okay, the electron beam can be deflected. The electron beam can be deflected by applying a magnetic field. Okay, perpendicular to the beam over a short distance along its path. The magnetic field will exert a force on electron in a direction at right angles to both the direction of motion of the electrons and the direction of a magnetic field. As a result, the electron beam emerging from the magnetic field makes an angle with its original direction. This type of deflection is known as magnetic deflection. Okay. To calculate the expression for magnetic deflection sensitivity, consider an electron beam AB. Coming from the electron gun acted upon by a uniform magnetic field of flux density V over a length L of its path, of its path. The magnetic field is applied perpendicular to the direction of flow of electrons so that the beam describes an arc BC. Okay, arc BC. Okay, then 1 minute. The path of the electrons remains circular within the magnetic field, and after leaving the magnetic field, the electrons move in a direction CD tangential to the circular arc at C. Let R be the radius of the circular arc BC. Let R be the radius of the circular arc ABC. Okay. If VA is the acceleration potential and V the velocity attained by the electron, then if VA is accelerating potential and small v velocity attained by the electron, then 1/2 mv square equal to E into VA. Okay, or V equal to under root of 2EVA upon M. This is the equation number first. Okay. If B is the magnetic flux density, then Lorentz force acting on the moving electron. Lorentz force acting on the electron is BeV. Okay, this is equation number second. Move in a circular path of radius r and is acted upon by a centripetal force mv square by r. Centripetal force is mv square by r. That is equation number third. Okay. These two forces given by relation second and third balance each other. These two forces given by relation second and third. Okay, balance each other. BeV equal to mv square by r. Okay, then r equal to mv by be. Okay, then substituting the value of v from equation number first, we get from equation number first we get r equal to m by be under root of 2EVA by m, that is 1 by b under root of 2mVA by e. This is equation number 4. On leaving the magnetic field at the point C, on leaving the magnetic field at the point C, the electron beam moves along the straight line. Move along the straight line. Okay, move along the straight line. Okay, move along the straight line CD. Move along the straight line CD and hits the screen at the point D. The straight line CD is tangential to the circular path BC. At point C. Now total deflection. Total deflection D is ED. That is EM plus MD. That is D1 plus D2. D1 plus D2. And if O is the center of the circular arc, okay, D and O is the center of the circular arc. Okay, if O is the center of the circular arc and theta the angle subtended by the arc, okay, and theta the angle subtended by the arc at O, at O and R its radius, then D1 equal to EM. D1 equal to EM equal to BN equal to BN equal to BN equal to OB minus ON. OB minus ON. Then this is R minus R cos theta. R minus R cos theta equal to R common 1 minus cos theta. This is the equation number 6. Okay. Also angle DCM. Angle DCM equal to angle DPE that is theta. Okay, so tan theta equal to D2 upon capital D. Okay, D2 upon capital D. Then D2 equal to D capital D tan theta, that is D theta when theta is small. Okay, theta is small. Also when theta is small, then theta equal to sin theta equal to L by R. This is equation number, and D2 equal to D into L by R. Okay, that is equation number 7. And equation number 7. And cos theta equal to 1 minus sin square theta power 1 by 2, that is 1 minus 1 upon 2 sin square theta equal to 1 minus theta square by 2 equal to 1 minus L square by 2 R square. From equation number 6, D1 equal to R1 minus cos theta equal to R1 minus 1 plus L square by 2 R square. Okay, that is R L square by 2 R square, that is L square by 2R. Okay, L square by 2R. Hence total deflection. Total deflection D equal to D1 plus D2 equal to L square by 2R plus D L by R equal to L by R L by 2 plus D. Okay, but L by 2 plus D equal to capital L, the distance of the screen from the midpoint of the field. The distance of the screen from the midpoint, midpoint of the field, okay. Total deflection, D equal to L capital L by R, okay. Substituting the value R from the equation number 4, we have substituting the value of R from equation number 4, we have D equal to L capital LB under root of E upon 2 MVA. Magnetic deflection sensitivity. Then magnetic deflection sensitivity, magnetic deflection sensitivity, SM equal to D by B equal to L capital L under root of E by 2 MVA. That is equation number 8. Okay. Importance of magnetic deflection sensitivity. Importance of magnetic deflection sensitivity, okay. Magnetic deflection sensitivity. The magnetic deflection sensitivity is inversely proportional to the magnetic deflection sensitivity SM is inversely proportional to under root of VA, okay. Whereas electrostatic deflection sensitivity is inversely proportional to VA. Where is static sensitivity deflection? Static sensitivity deflection is inversely proportional to 1 upon VA. Therefore, the electric deflection sensitivity decreases more rapidly with increase in anode voltage than magnetic deflection sensitivity, as the loss of magnetic sensitivity is smaller as VA is increased. For greater spot brightness, it is customary to use magnetic deflection in TV system and radar indicator, where high spot brightness is required. The electric deflection suffers a larger deflection defocusing is as the angle of deflection is increased, the spot on the screen tends to the distorted and enlarged, but this is much less in the case of magnetic deflection even for large deflection angles. The greater allowable deflection angle decreases the tube length for a given diameter, hence magnetic deflection is desirable in cathode ray tube used in television, okay. Importance of electrostatic deflection sensitivity. Importance of electrostatic deflection sensitivity, okay. The electrostatic deflection requires little power for deflection, while large power is consumed in the electromagnets required for magnetic deflection. Hence, electrostatic deflection is used in common purpose oscilloscopes. Moreover, electrostatic deflection can be conventionally used for high frequencies. Okay, next heading, dual beam CRO, cathode ray tube. Okay, dual beam CRO.